Today we're going to talk about optimization problems. Optimization problems is a way to use the derivative to find critical points to either maximize or minimize some sort of situation. So we're going to start off with a basic one about numbers. So if I have two numbers and I say the sum is 288 and I want to maximize the product, I always put a little star, notate somehow what I want to maximize or minimize, because that is going to be the function that I find the derivative of and set equal to 0 and get my critical points. I'm going to let x and y represent my two numbers. If the sum is 288, that's just x plus y equals 288. The product means multiply, product equals x times y. This is what I want to maximize. I cannot take the derivative at this point with two different variables. So I'm going to come back and use this first equation and solve for y. Y equals 288 minus x, and substitute in. So now I've got a function that I can take the derivative of and find critical numbers. So my product, I'm going to distribute first, 288x minus x squared. I take the derivative, and that's 288 minus 2x. Just like I always do when I want to find a maximum or a minimum, I set the derivative equal to 0. And that gives me x is 144. That's my first number. I want to check and make sure that that is in fact a maximum. So I'm going to do just what I did previously. I'm going to make up a sign chart and substitute into my derivative function and see what's going on. So my derivative function is 288 minus 2x. The number I care about is 144. That's where p prime equals 0. If I try, let's just try 100, say, a number less than 144. 2 times 100 is 200. 288 minus 200 is positive. So my derivative is positive. I'm going to try 150. 288 minus 2 times 150. 2 times 150 is 300. 288 minus 300 is negative. So I do have a max. My derivative goes from positive to negative. So if x is 144, I can figure out y by substituting in 288 minus 144. And if I want to know what the actual maximum product is, that's going to be 144 times 144, or 144 squared, which is 20,736. So that's just a basic problem to get us started. Let's do one that's a little bit more interesting. This is a very common type of problem. We want to maximize the volume when we have a sheet of metal that's 48 by 48 inches. And what we're going to do is cut the corners out and fold up the sides so that I have a box without a top. So I made a little model. I've cut the corners out. Each corner is a square because we want the top to be level. And then I fold that up and I end up with a box. To get an idea of what's going on, I'm going to use a technique I always use. I'm going to try a couple of numbers. So if the side of each square that I cut out is 1, so that 1 is actually going to give me the height of my box. The bottom of the box is a square. So to find the volume, I'm going to do the side that's left, side squared, times the height. So the side of the square that's left is going to be 48 minus 2 times 1, because I took out this one and this one. So that leaves me 46. The volume is 1 times 46 squared. And if I multiply that out, I get 2,116 cubic inches. I don't really have an idea now if that's good or bad, so I'm going to try a different number. I'm going to try a little bit bigger number, in this case 4. So if I cut out a side of the, so that the side of the square is 4, and I fold that up, what's left in here is 48 minus 2 times 4, which is 40. My volume is going to be 4 times 40 squared, and that gives me 6,400 cubic inches. Definitely better. I don't know yet if that's going to be the best though, and I don't want to try every option because there's an infinite number of options. But I've got an idea of what's going on. So if I fold out side x, I'm going to go back to what I did here, and instead of the 4 and instead of the 1, I'm going to put an x, because that's what I did every time. So this would be 48 minus 2x. The volume would be x, which was my height, times 48 minus 2x, the quantity squared. I've got a function now that I can maximize. So the volume is x times 48 minus 2x, the quantity squared. I'm going to use the product rule to take the derivative of this. You also could multiply it all out and go from there. So derivative of x is 1 times 48 minus 2x, the quantity squared. When I get to the derivative of the second term, I have to do a chain rule. So it's 2 times 48 minus 2x times negative 2, my derivative of the inside, times my first term. I still don't want to multiply this whole thing out, but that's okay because I see that I have a greatest common factor of 48 minus 2x that I can bring out front. So my v prime, I'm going to factor out the 48 minus 2x. That will leave me with 1, and this term will cancel because we brought it out front. So I'm left with 48 minus 2x. I've got 2 times negative 2 times x, which is minus 4x. So my v prime is 48 minus 2x times 48 minus 6x. I'm going to set each of those terms equal to 0. If I solve this first one, I get x equals 24. But I know that cannot be the case, because if I went to 24, what I would end up doing is just folding my whole box in half, and I would not even have a box. I would fold my metal in half, and I would not even have something I could find the volume of. If I solve this, I get x equals 8. So that means the dimensions would be 8. 2 times 8 is 16. So if I do 48 minus 16, that gives me 32. So the dimensions would be 8 by 32 by 32, or 8 times 32 squared. You can multiply that out and find the volume. If I want to be sure that that is the maximum value, again, I'm going to look at my derivative here. And I'm going to substitute in and see what happens at 8. So when I make my sign chart, I've got 0, I've got 8, I've got 20, 24. We figured out that can't happen because that does not give us a box. So my volume, the derivative of my volume is 48 minus 2x times 48 minus 6x. If I substitute in 0, I get 48 times 48, definitely positive. If I substitute, say, 10, 48 minus 20 is positive, 48 minus 60 is negative. So indeed, x equals 8 was where my maximum occurred. And my dimensions were 8 by 32 by 32, and if I multiply that out, that would give me the maximum volume.